So I would like to talk about the diameter width ratio for complete and pseudo-complete sets. So this is a joint work with my advisors, Renan Brandenberg and Bernardo González Merino, which I did during my PhD in the Technical University of München. Please, the next one. So we start with some motivation, which is average length. So imagine you want to climb up a mountain and you are interested about the length of your path, so the distance. Then you can fix your point X to be as the bottom point of the mountain and Y is the top one. And then the length of the distance can be calculated as the gauge function of the vector X minus Y with respect to some unit ball C. If you take the unit ball C, please wait, unit ball C, no. I will say you when it's next, okay? So if you take C to be the Euclidean ball, then it's just the Euclidean norm. Also, you can take any convex compact set which is symmetric, and this will induce your norm. But in general, if you're taking care about the direction, then you can take also in account some non-symmetric body C. So let us see how we can average this gauge function with respect to some non-symmetric convex sets. So please, next slide. So we need some notations. The first notation is the Minkowski sum. We take some sets A and B, and the Minkowski sum is just a vector sum. So you take a point A from A and B from B. Here you have a picture, a yellow triangle and a blue triangle. And if you take the vector sum of them, you end up in this nice hexagon green. Please, next. The next notation we need is a polar body. So the polar body you can understand as a generalization of the inverse. So if you have a number, you can take a number A and the inverse 1 over A. And for generalization, we consider the polar body. So you have some convex compact set K, and you consider the body K polar, which is defined as such that the scalar product of any point from K with a new point is less or equal 1. If your body K is just the Euclidean ball, then naturally the polar body is also Euclidean ball, but now rescaled. So if the radius of your polar ball of your body K was R, then of the polar one is 1 over R. And this is why you talk about the inverse of some body. So please, next. So now we can take the sum of two sets, and we can also take something that is like the inverse of the set. So let's return to the motivation. We wanted to know the distance from point X to point Y, which we calculated using the definition of the gauge function. For a body C, and the body C in this case we can take as a simplex. So in the two-dimensional case, it's just a triangle. Let's see. If you want to find the distance from X to Y, you take the black C and rescale it such that the full segment XY will be contained in the body C. Now let's think about what is the distance from Y to X. This is the same as taking the gauge with respect to minus C, but also you can just change the arguments and you get that it is a gauge function of the X minus Y with respect to minus C, which is on the picture denoted as the dashed set. And you see that then the distance from the bottom to the top is twice as long as from the top to the bottom. But if you're talking about some applications, you don't need to have the gauge dependent on the direction. So you want to have your distance to be in all the directions the same. So what you do, you want to approximate your gauge function with some norms. So you want to understand what can be the symmetrizations of C, which we can use as the unit ball of our new norm. Please, next. And here you can see which symmetrizations we are taking care of. So we take the distance from X to Y, from Y to X, and just average them. The natural average is taking the maximum of the two distances. One can see that is this actually a norm of X minus Y with a unit ball C intersected with minus C, which we call the minimum of the set C and minus C. On the picture, this is the blue hexagon. But this is not the only average of the two distances from x to y and y to x. We can take also the arithmetic mean. This is the second line. And we end up with another norm, which is the so-called harmonic mean of C and minus C. And here you have that is C polar minus C polar over 2 and again polar. If thinking again about the polarization as the inversion, you have something like 1 over C minus 1 over C over 2, and again this to the power minus 1, which is a kind of generalization of the harmonic mean for numbers. So one can also think about other symmetrizations. The third symmetrization is given in the third line, and this is we can induce a norm by the body C minus C half. Unfortunately, you cannot represent this in terms of the gauge functions of C and minus C. On the picture, this is the brown hexagon. And the next symmetrization we're taking care of is a convex hull of C and minus C. So you take the union, and because you want to have your new set convex, you take also the convex hull. On the picture, this is a green one. So now you're not dealing with the gauge with respect to the body C, but you have induced a norm with a unit ball that is given by the one of the four symmetrizations. The minimum, so the intersection of C and minus C, the harmonic mean, the arithmetic mean, or the convex hull, which is considered as a maximum. And you see that all of the symmetrizations are included one each other. So we will now study this in details. Please, next. So let's compare this to the one-dimensional case. So if you have two positive numbers, you can write down the arithmetic harmonic mean in an equation, which says that the harmonic mean is less or equal to the arithmetic mean. And also you can extend it by writing that the minimum and the maximum on both sides. Oops. Okay, next, please. And the same we can do with convex sets. We only have to require that X is in the interior of both to don't have trouble with intersection. So here you see that the minimum of two sets is A intersected B, corresponds also to the one-dimensional K as a minimum. Then you have the harmonic mean, the arithmetic mean, and the convex hull. And the same way as the arithmetic harmonic mean for the numbers, you see that they are included one in each other. So you have four different means, all of them building up a chain of inclusions. Please, next. So we have this chain of inclusions, but is this chain optimal? So when you have the inequality, you always want to have it in an optimal way. Here we're talking this in a case of inclusion. So we want to understand if this inclusion is optimal. What we mean optimal, we mean that the body K is contained in C, and also it is not contained in any smaller version of C, which is shown here on the picture. So please, next. We study now the optimalities of this inclusion. First, we show that the minimum is always optimally contained in the harmonic mean. And also we have shown that the arithmetic mean is always optimally contained in the convex hull. This is the first inclusion on the left and the last inclusion on the right. Here is a picture that we studied in the motivation. So the optimality you can see on the left side is the one between the blue set and the yellow set. You see that the touching points doesn't allow any escalation smaller. And also from the arithmetic mean and the convex hull, so the right-hand side inclusion is the one that corresponds on the picture to the set that is brown and green. You see that they are also optimal contained. And this is this holds for any convex set. But what is interesting is we want also to study what is happening between the two sets in the middle, so the harmonic mean and the arithmetic mean. On the picture, this corresponds to the yellow and the brown. As we see for the case of the triangle, they are not optimally contained, which means that the brown one can be rescaled by a smaller factor such that the yellow is still contained. So we would like to study this in more detail. Please, next. Exactly. So the question is, we want to study the inclusion that is in the middle between the harmonic mean and the arithmetic, and also between the minimum and the maximum. Please, next. To do this, we take into account a functional that is called the Minkowski symmetry. The Minkowski symmetry is defined for any convex set and is defined in a way that is the minimum of the row such that C is contained in the row times minus C. For minus C, you take the body C and you rotate it by 180 degrees. So here on the picture, what do? You have the blue set K and you want to find what is the factor S, so the Minkowski symmetry of the set. So you take the rotated version of minus K and rescale it such that K will be contained in the set S of minus K. What is interesting about the functional is that it can get values only between 1 and n, when n is a dimension of the space. And also it's 1 if and only if K is symmetric, so meaning K is equal to minus K, and the maximum value, S is equal to n, is obtained if and only if your set is a simplex. We also take into account the center of the set to be the Minkowski center, which is the translation needed to get into the definition of the Minkowski symmetry. Please, next. So let's remember what was the question. We want to study when the minimum is optimal contained in the maximum. So C intersected with minus C has to be optimal contained in convex hull of C and minus C. So we define the factor which allows us this containment to be optimal. And now we define the minimum and maximum of this factor to be lambda 1 and lambda 2. And we want to find the regions of the possible alphas depending on the asymmetry S of the considered set. Please, next. This is a result that we got for the two-dimensional case. We have shown the complete regions of this possible factor alpha. We have shown that this is bounded by 1 from above and also by the function S over S squared minus 1. Here S is the symmetry value of the considered set, and the lower bound is 2 over S plus 1. And we also have shown this diagram is filled. Please, next. Let us take a look about the extreme cases. So for the lower bound of the parameter alpha, which is 2 over S plus over 1, we consider the set C to be the simplex intersected with minus S times S. Here you have on the picture the two-dimensional case when you consider it as a triangle. Please, next. Here is a picture that shows you all the symmetrizations of the considered set. So you have that the minimum is a convex hull of the black dots. The yellow set is a harmonic mean. The blue set is a arithmetic mean. And the red set is the maximum, so the convex hull. So from the picture, you can see that in order to get the optimality between the intersection and the convex hull, so with the convex hull of the black dots and the red set, you need the factor 2 over S plus 1. Please, next. Let us now consider the upper bound for the parameter alpha. The upper bound for the parameter alpha was a maximum of 1 and S over squared minus 1. And the extreme set is a pentagon, which you can see on the screen. So you have the special pentagon is the extreme case. Please, next. Here you have another picture which shows you all the different symmetrizations for this considered pentagon, which by the shapes remembers a house, so we call it the house. And the colors correspond to the same. So the yellow one is a harmonic mean, blue arithmetic mean, and the red one is a convex hull. Please, next. What is also interesting is that we have the breaking point in the upper bound of the parameter alpha. And this happens when the value of a symmetry S is exactly the golden ratio of phi. So 1 plus square root of 5 over 2. Let us discuss this breaking point in more details. Please, next. So we have shown that the parameter alpha cannot be 1 if the asymmetry is greater than the golden ratio. And also, if the asymmetry is exactly the golden ratio, then the extreme body is unique. And this is exactly the pentagon that you can see on the screen. So because this pentagon has the shape of a house and the symmetry of it is the golden ratio, we call it the golden house. So this is a unique extreme body. Please, next. So let's talk now about how we apply the parameter alpha for another interesting topic, which is a constant width sets. So the constant width sets are sets which have an interesting property that they can roll in any direction, like balls, but they don't have the shape of Euclidean balls. So this means if you sandwich them between two flat surfaces, you can rotate them in any direction like you want. This is because the breadth in any direction is the same. Please, next. So the breadth is defined like here. For the definition of the breadth, we consider the ratio between the support function of the body k minus k and over the support function of c. So, and for the breadth, you can take it in any direction, and you can also define the minimum breadth and the maximum breadth. The minimum breadth is the width, and the maximum breadth is the diameter. So in general, the minimum, so the width and the diameter are not the same. But because we have that the breadth is in any direction the same, you have that the width and the diameter for constant width set is actually equal. Please, next. So you have equality between them. And here you have a picture that shows you an example of the constant width set. So let's talk about the one of the triangle. This is called the Rouleau triangle. What is interesting, so let's sandwich this set between two parallel hyperplanes in any direction, and you will get that the distance between those hyperplanes is the same, which means that they are constant width sets. Let's do next. But it's very difficult to study the constant width sets. So people came up with a broader family of sets, which is called the complete sets. For the complete sets, we have that the diameter of any bigger set is strictly greater than the diameter of the body k, which means taking any point out of your diameter and include it as a convex hull with your considered body k will enlarge the diameter in this direction. So complete sets, constant width sets are complete sets, but there are complete sets which are not of constant width. For the complete sets, we have the nice property that taking any set, we can find an algorithm how to provide you with a completion. So given a set, you can always find a complete set, which is not possible for the constant width sets. What is but interesting is how good is the approximation with a complete set for the constant width sets. In other terms, we would like to know how big is the ratio between the diameter and the width for the complete sets. So we know that for the constant width it's 1, and now we want to bound it for complete sets. Please, next. And this we have done in this result. We have proven that if K is a complete set with respect to some set C, and the Minkowski asymmetry of the set is S, then the diameter width ratio is bounded from above by the fraction s over 1 over 2. So as S is a symmetry factor, remember that if your set is symmetric, then it's 1. So if you have that K is symmetric, then this becomes just 1, which makes sense, because if it is symmetric, then the only set you can consider is K to be equal to C. And if the biggest fraction you can get is n plus 1 over 2, which happens if and only if your set K is a simplex. And this is a worst case. And also we have shown that this bound is sharp, meaning that we can provide bodies, which are extreme cases, for which this ratio holds with equality. So please next. So that's everything. Sorry for this technical issue, and thank you for your attention.